Everyone, this is our briefing to help us answer the question, what do we know about Mars? And here to help answer that question is Michael Meyer, the lead scientist for the Mars Exploration Program, Bethany Ehlmann, scientist from the Jet Propulsion Laboratory, assistant professor at the California Institute of Technology, and John Grotzinger, the project scientist for the Mars Laboratory at the California Institute of Technology. And we'll begin first with Michael Meyer. Michael?
Well, thank you, George. For millennia, humans have been wondering about the red planet and studying it, and it's only recently that we've actually been able to go there and look. In 1976, we sent two missions there, the Viking missions. Both were orbiter and lander, and we sent them to the red planet. If I could have the first slide, please. So Viking landed, and this is from Viking 2, and it shows a cold, barren, dry, apparently dead planet. And as you might imagine, the enthusiasm for Mars exploration kind of took a plummet. But interestingly enough, during the same period of time, we found in the subsurface ocean life in scalding hot hydrothermal vents. And that started a whole line of study of looking at life in extreme environments. And through that study, we came to learn that life is capable of adapting to all sorts of environments where it seemed like the only real necessary ingredient would be liquid water. This was encouraging to the broad scientific community in understanding that there may be more places where life is possible than we originally thought. So we began the modern era of Mars exploration. So in 2 decades later, 1996, we sent the Mars Global Surveyor. Could I show the next slide? And what this slide shows is the missions that we've had sent to Mars since Mars Global Surveyor. And with that, we've had orbiters and landers. And with each successive mission, we've been able to increase the spectral and spatial resolution of our look at the red planet. And we've learned so much more. We've learned that Mars is a dynamic planet. We've learned that it has a history where it was warm and wet at the same time that life started here on Earth. And we know that it's gone through a massive transition from that more benign planet of early on to what it is today. And so we're actually here to give you a rundown on some of the things that we've learned in the last 10, 15 years about the red planet that encourage us to think that Mars is worth exploring for many different reasons, including the potential of having been habitable, at least in its past. George?
Thank you, Michael. And now to Bethany Ehlmann, the scientist from the Jet Propulsion Laboratory and assistant professor from the California Institute of Technology. Bethany.
So I have the privilege of talking to you about some of the discoveries from this flotilla of missions that we've sent to Mars over the past decade. And if we can start with the first graphic, I'm going to begin the story with what we know about Mars as it is today. So these are the top highlights of what we know about Mars today. And so Mars today on this graphic is what you see in the top left of this picture. Mars, like Earth, is tilted on its axis, and as it's spinning like a top. So Mars has seasons. You can see the two polar ice caps at the north and south of Mars. But Mars, unlike Earth, is not stable around its spinning axis. So what happens is that Mars' axis tilts. Okay, and what we found through a combination of modeling and observations of the surface is that this results in ice ages on modern-day Mars. You can see that when Mars is tilted more extremely than it is today, ice builds up around the equator. When Mars sort of straightens out along its axis, the poles grow in size. So this changing distribution of ice is one of the emerging stories that's come out of the work of the recent decades. And if we go to the next slide, we see evidence of this. The HiRISE camera on the Mars Reconnaissance Orbiter is able to examine the surface at very high resolution. And what we've found is that impact craters that impact into the mid-latitudes of Mars have excavated ice from beneath the surface. And that's what you see in this image here, ice associated with these small craters. Now, this ice isn't stable at the surface. It's a relic of these past tilts and changes in Mars's obliquity. And so if we look back at this on the order of a few weeks and a few months at the same spot, the ice is gone, but it's a hint at past climate change. If we head to the next graphic, the other hint of this changing dynamic modern Mars is in this recent discovery, where you can see from right to left these dark streaks emanating from the walls of a crater. These streaks were recently, in a recent paper by Alfred McEwen et al., the best hypothesis we have to explain those streaks is that they're formed by short-term discharge of briny waters when modern-day Mars heats up during the summer. For a brief period in time, this ephemeral, quick period of time, we may in fact have salty waters on Mars. So if we go to the next graphic, I've talked to you about modern Mars, a story of ice, very, very, very short-term rare water. But if we look at ancient Mars, this is a topographic map where red is high elevations, blue is low elevations. We're looking at the Mars globe, and I've oriented it so that you can see Mars has these enormous outflow channels and valleys that flow out, where water previously flowed out into the northern lowlands. That's that blue low depression toward the left-hand side of the screen. So liquid water was not short-term in the past. We know that it had a role in carving out these large channels. And if we head to the next graphic, it also had a role in depositing sediments within craters. Now this is an image that's a combination of some of the data sets from the Mars Reconnaissance Orbiter, the high-resolution camera, the context imager, and then overlaying are colors from the CRISM infrared spectrometer. And these colors, along with the spectra from pixels in this image, allow us to get at the composition of these sedimentary materials that were carried by the water. And now the key color here is the green, because the green materials have been identified as clays and carbonates. Now these are minerals that form in the presence of liquid water, and the clays in particular indicate the long-term presence of water interacting with the rocks, causing alteration of minerals. Clay minerals also have water in their structure. And if we go to the next graphic, we see these clay minerals and other hydrated minerals, so minerals with water in the structure, in different geological settings throughout the planet. This is just another example that we're able to get at now with this high spatial and spectral resolution of Mars, where we can pick out in the walls of this crater, kind of like the pages in a book, two different pages in Mars history, where early in Mars history we had an alteration, that process that formed iron magnesium clays, maybe not so much water flushing through, possibly in the subsurface. But on the top we have this unit with a higher degree of leaching forming aluminum clay. So two distinct periods in Mars history recorded in these strata. If we go to the next, I'm just going to provide another example, because here we go from clay minerals. Clay minerals form from long-term chemical interaction of water with rock, and they're the green color. Now, the pink color are sulfate minerals, again, salt minerals identified through spectroscopy. Now, so this is just a subset, a small snapshot from a crater that's over 100 miles in diameter. And what we see when we look around that crater is this bathtub ring of salts. So in this crater, it was once filled with water, and upon evaporation deposited these sulfates sort of ringing around afterwards. What does this all mean? So if we go to the next graphic, what we think this means is that we can trace a progression in Mars history through both minerals and by careful examination of rock strata in a few key locations across the planet. Now on the bottom are Noachian, Hesperian, Amazonian. Their names you'll hear over the course of other press briefings, which are the traditional divisions in Mars time. What we think we see as we move from the Noachian is this clay era where there was abundant water chemically interacting with rocks. We move that and then into a drying period where you get sulfate salts deposited as the water begins to go away at the surface. And then you're in cold, modern Mars, where ice is the story, not liquid water. So there's this fundamental transition between the Noachian and the Amazonian, between the era of clays to the era of sulfates to the era of anhydrous minerals, where water doesn't appear to play a role. And it's that critical period that's spanned by the sediments at Gale Crater. We want to understand those transitions, so that's why we're headed there.
Thank you very much. And our next briefer is John Grotzinger, the project scientist for Mars Science Laboratory from the California Institute of Technology. John.
Great. Thanks, George. So what I'd like to do is take you back again to a few decades ago, and if we can have the first graphic. One of the motivating reasons for the Viking mission to land and look for evidence of life on the surface of Mars was a discovery of the channel network systems that you see here. These have been studied for decades now. I think it's safe to say that virtually the vast majority of the science community believes that these channels were cut by flowing water, emerging from the surface, subsurface, maybe flowing across the surface. But it's these channel systems that originally attracted so much attention for Mars. Now, in the more recent decade, there have been some spectacular discoveries that sort of fill out the rest of the story. Because if you look at these channels, it's natural to ask, if water was flowing, where would it take all the materials that were eroded away to create the canyons? So if you go to the next display item, what we see here is a delta called Eberswald Delta. It was one of the potential landing sites for the mission. And it's at the end of one of these channel networks. And so we see all the material that got eroded by water here being deposited in water as a delta that almost everybody can recognize. And this is really amazing because in addition to this, there was also the discovery of clay minerals here. So we're beginning to see a more balanced picture of Mars, one where you have source areas that represent the interaction of water with rock to produce sedimentary materials that contain alteration products like clays, and then they get transported down river systems to form things like deltas that would have accumulated in bodies of standing water. And this is very attractive from a habitability point of view. And it creates the basis then for Mars Science Laboratory to have had a very exciting landing site selection process. So if we go to the next one, now we're going to jump up here more recently within the last 7 years, the discoveries by the rover Opportunity and the Mars Exploration Rover mission. And here we see a number of very important aspects that take us into our understanding of modern Mars. One is that we see layered rock, sedimentary rock. And the sedimentary rock on Mars we view in an analogous way to sedimentary rocks on Earth, which are the principal repository for all the records of life on Earth. And while Mars Science Laboratory is not a life detection mission, we are on a mission to investigate the building blocks of life, important chemical elements, and also potentially look for organic compounds. And when you have what a geologist calls a model like this, where you can look at the rocks and see that you had ancient sand dunes, environments where there was ancient groundwater, and then environments where you had ancient streams, this gives you a whole diversity of potentially different habitats. This is just one example on Mars. You can go back to the locations that Bethany was talking about, the very ancient Mars, and you see a different type of geological history and a very different type of potentially habitable environments. So we're just on the cusp of beginning to come up with a whole range of these possibilities for us to explore into the future. Okay, so in the next one, now we take us into, as Bethany mentioned, there were the three eras where you went from dominantly clays, time when weathering, alteration of water produced clays, to a time when alteration of water produced a lot of sulfate minerals, to a time when apparently there were not many hydrated minerals that were formed, yet we still see the accumulation of sedimentary materials. And you might ask, what do you learn about Mars in the absence of water or in the absence of a potentially habitable environment for life if it had evolved on Mars? And this is a beautiful example of that. You see these very well organized strata. This is like a heartbeat, except this is the heartbeat of the planet's climate cycle. So just like on Earth we're very interested in climate change, on Mars we see this very rhythmic alternation of layers that creates a really spectacular record of past climate change on Mars. And then that takes us to the era that Bethany talked about first, where Mars is dominated more by ice and a very cold climate and atmospheric processes and transport of sediments by wind rather than water. So we can see in the rock record these different histories. Okay, so now if we go to the next one, What we see here is our destination for Mars Science Laboratory. This is Gale Crater. You'll hear a lot about it tomorrow at the press briefing tomorrow. There's a crater about 150 kilometers in diameter. That's about as big as the Los Angeles Basin, surrounded by the mountains that ring the Los Angeles Basin. And right there in the middle of it is a mountain about 5 kilometers high. That's as high as Mount Whitney, which is the tallest mountain in the lower 48 states. And if you go from the yellow dot, which is in the center of our landing ellipse, we have the ability to traverse in our mission through the first few hundred meters of strata that you see there. And then eventually, over an extended mission, it might be possible to go to the top of that mound. But the important thing I wanted to say about the mound today, to sort of lock in some of the points that we've been talking about, at the base of the mound, you see strata that are composed of clays and sulfates. As you go farther up the mound, you see strata that are composed of dominantly sulfates. And then as you get above the first 500 meters or so, you then go into strata that don't have hydrated minerals. They seem to be composed of these rhythmites from the drier time of Mars. So in one location, we can drive the rover through all these successive different environments and sample these various periods in the history of Mars that we've talked about. So I'll turn it back to George.
All right. Thanks very much. We're ready now to take questions. So please give your name and affiliation when the microphone comes to you, and we'll start right here in the front with Ken.
Hi, Ken Kramer for Spaceflight Magazine. For Bethany and anyone else who wants to answer, please, a couple of questions. Can you describe the clays, how widespread they are on Mars, and the sulfates? Are they very narrow, or are they pretty widespread?
Right. So I should say that clays and sulfates were something that weren't even discovered until 2004 with the Mars Express mission from Europe. So they'd eluded detection so far, and that's because the exposures where we're able to see them are very small. And it makes sense if you think about the fact that they're ancient, and because they're ancient, they're buried by later materials. So with this high spatial resolution, we're able to see them. And where do we see them? So clays, to the extent that we are able to figure it out, they seem to be globally widespread, but frequently buried. And the way they're exposed often is in impact craters, where, again, we punch through the surface and these clays are thrown out for us to be able to see them. We also have a few places where tectonic activity has exposed a nice, thick stratigraphic section with the clays. But the clays do appear to be global. The sulfates also are regionally global, if that makes sense. There are a few regions scattered throughout the planet where we see sulfates. It appears that some work on hydrologic modeling groundwater flow through Mars, and orbital detections of sulfates are starting to converge, where it looks like where we see the sulfates are these zones where it's predicted that groundwaters would be upwelling and reaching the surface.
Okay. And for John, could you tell me, I think you said these channels you believe most are by water, formed by water. So do you say that about Valles Marineris? It's mostly water? You don't think it's carbon dioxide? And also, how long is that distance from the yellow dot to the red dot? How quickly could you drive the rover?
Right. A couple of questions there. I think that, for a long time, as long as people have seen the channels, there's been a discussion about what the liquid was that carved them out. And as I said, I think that this is now stabilized on water as being the most likely material, and that's been bolstered recently by the discovery of hydrated minerals that do occur as transport weathering products in these channels. It was a prediction of that model. It was observed independently, and I think it shores the whole thing up. The second question about Valles Marineris. Valles Marineris is a different feature. It's not produced by erosion. It's dominantly produced by tectonic processes that involve big crustal motions that drop blocks down. And at the base of Valles Marineris, you do get thick successions of sulfates. One of the attractions of Gale to us is that without being able to fly into Valles Marineris, we capture a lot of the interest that you would get in going to Valles Marineris, because the bottom layers in Gale Crater are composed dominantly of sulfates, and they sit in a very low topographic depression. lower than the floor of Valles Marineris. So it's not the same as Valles Marineris, but it's maybe as close as you can get. And then the last question about the distance, our landing ellipse is about 20 kilometers in diameter, so we would drive outside of the landing ellipse on the order of about 12 kilometers to get to the first well-developed sulfate deposits and clays.
Okay, we have a question here in the back. Did you have a question?
Yes.
Okay.
It's Chris Haber, United Television Network. I was wondering with the recent discovery of the shifting the sand dunes, are you planning on using Curiosity if there's anything on board that you might be able to investigate further with the existing equipment that's already built into the rover?
Yeah. That would be a good question to bring up again tomorrow, because we'll have the principal investigator of the camera here, and that's one of his real interests. And so we have the ability to measure the wind speed on Curiosity, what direction the wind is blowing in, and then make measurements of the surface topography of the dunes and see if sand is being transported. We should be able to do that.
Marcia?
Marcia Dunn, Associated Press, probably for Dr. Meyer, but I'm not sure. Of the previous Mars missions, the several dozen that there have been, how many besides this one have actually looked directly or indirectly at the life issue? And what have you learned so far that this will build upon?
Well, I actually like to call Curiosity the first astrobiology mission since Viking. And basically that's because we're sending a gas chromatograph mass spectrometer, which can look for organics and characterize them. And essentially it's similar, much better, but similar to the instrument that was sent on Viking. Here the huge advantage is that you can rove to wherever you think is the best thing to measure.
So there's been this gap then essentially in your mind.
Phoenix had a gas chromatograph mass spec on it that could have measured organics if there was sufficient amount, but it couldn't move around, and is also on the northern polar layer terrain. So in many ways its goal was pointed more toward understanding the formation of the layered terrain and what the polar areas are like. So Curiosity, I think, is really the first one since Viking to approach the life question. Now, I should be clear that it doesn't have a life detection instrument on it, in the sense that a camera is not a life detection instrument unless something hops in front of it. So the capability of SAM, the sample analysis at Mars, which is the gas chromatograph mass spec, is that it can look at organics and characterize them and make you more interested in Mars and what secrets it might hold. But unless you're extremely lucky, it's not going to tell you whether or not you found evidence of life.
Can I ask another question? What is it about Mars that makes it so treacherous getting there? So many missions have failed, including one in Earth orbit right now. What is it about Mars that makes it so tricky, so difficult to get to?
Well, one theory is gremlins. The other is just I'm not sure why we've been that unlucky, and it may be that early on in planetary exploration, Mars was a target such that as our spacefaring agencies were coming up to speed to how to do planetary missions, their first target was Mars. So there's a lot of failures early on, and just with how do rockets work, how do you get there. So I think there was a big learning curve, and now we're just running into Mars is difficult, and so many things have to go right for a mission to work. But we have a much better track record than we did in the 70s.
Dan?
Dan Billow from WESH-TV. On the time-lapse photo you had that looked so much like surface water, give me a ballpark estimate, if you can, on how long that might persist, hours or days, and if you have any idea. And would you discuss a little bit more about to what extent the planet has kind of a subsurface layer of ice? Do you think that that's the case?
Yeah, I'll take that. So water, liquid water, is not stable on the surface of Mars today. So as for how long it sticks around, well, it's how long it takes for it to evaporate. So we're probably talking on the order of a few minutes. But what happens when that water is at the surface, it causes all these noticeable geological changes that we can then track. But we're talking really short periods of time.
But those features form and lengthen over a Mars. It starts, kind of in the spring, goes through the summer, and then they disappear in the fall. And it's happened on successive seasons. So although liquid water at the surface may be very short time, the moisture that's causing those features to form lasts over a whole season.
And a subsurface layer of ice or water, what are your thoughts on that?
Yeah, the thought is that it's a subsurface layer of ice is probably the most likely source for this water. And one of the things that may be causing it to melt periodically is the presence of salts, which just like you throw salt on the road in the winter to get the snow to melt, in those areas where there's a particularly high concentration of chloride salts, you also, those may be the areas where preferentially you get these slope streaks to form over the course of the season.
And just one more, I'm trying to get an idea, if you have an idea, of what the extent of that might be. Is there an ocean of that water, or a little bit, or a lot, or what,
Well, if we're talking ice and we're considering the entire subsurface of Mars, there's probably at least a shallow sea's worth of water in ice form beneath the surface. But when we're talking about how much is available in liquid form, it's only these ephemeral, short-lived slope streaks that appear to be occurring over the course of a season.
Anyone have any follow-ups? All right. In that event, just a little bit of a programming note. We have 2 Mars briefings tomorrow. At 1 o'clock, we'll have a briefing on looking for signs of life in the universe. And then following at 2 o'clock will be our Mars Science Laboratory science briefing. So if you'll join us for those, 1 and 2 p.m. Eastern Time. And that will conclude this briefing. Thank you very much for coming.
Thanks, George.